collaborators for like on the works that we have done so far last few years. Can you hear me right? Can you hear me right? Yeah. So basically, in the last few years, our group and also our collaborators focus on understanding each of experts in like massive AI models. So perhaps you may not know about the topics, but this is very important and was used in industry nowadays to scale up like the massive AI models. So I will introduce like a couple of works that we have ongoing with my university and also with like industry at the moment. Before I go into the details, I also want to briefly mention definitions of mutual experts. So the idea is very simple. So if you're familiar with machine learning, the idea is like we try to combine like multiple experts, right, using some kind of like mechanism like a gating function to somehow like form a more complex and accurate models. Let's say in this room, right, we have people expertise in like machine learning, in math, right, in computer science. So we try to combine the strength of our people together to have like very like strong and like unique right, like comprehensive person. So it's been like, let's say if you have an image, right, of multiple areas like face, nose, hands, so on, right? The idea is that we have one expert specialized in one areas of the image. So it's quite different from the traditional ways when we just basically proceed on pixels to the same like models. But here we try to use multiple experts specialized in different areas of the image. The idea is because we want to make sure like we can scale up the models by doing that. And that ideas were widely used in industry last few years, basically to form importance. The first one is like to scale up the AI models. The second thing is like to improve the safety of AI models. And the idea is like to actually account for the multi-modalities. We have different type data, like image, text, time series, and so on. It's been like each expert we always handle one type data. And finally, we also care about performance. But hope that when you actually you reach an expert, we can improve the performance of models. So these are like perhaps the four key directions that in the area at the moment. And to give you some motivation, I also want to show you like some applications of these models. The first one I mentioned is how we will use like each expert to scale up like these massive AI models. Let's say, I guess like everyone know about GPT, right? That GPT and GPT-9 from Google and also Microsoft. So these models, they actually utilize this for experts. So the idea is that you have a huge and models, right? Basically like a billions number of parameters. So it's basically very hard to store in memories, right? And when you scale further, let's say at the moment, we even had models with like 1,000 million parameters, and it's impossible to use, right? That's why the idea is like, we think about, we have a pointer. I can show you. So the idea is like, let me see this one, right? The idea is like, basically in the traditional models, we only have like one feed forward, I mean FFN here, feed forward, right, layer. So if we only have one feed forward layers, then to scale up the models it become very challenging because on the parameters going to be on that feed forward model only. So the idea is like they break that into like smaller chunks of models. Let's say you have like feed forward 1, 2, 3, 4, and 5. Right? So let's say you have 1 billion parameters and you want to scale up to 10 billions. So they have like 1 billion for each feed forward layer. Right? And then they consider only the sparse combinations of these feed forward layer. Let's say you have like 10 billion parameters for this layer. You mean like you have 10 feed forward neural networks and one have 1 billion. But then to scale up the models, they consider like only the best one when they train the models. This means that even you have like 10 billion parameters, but you only activate 1 billion to train. This means like even you have like very huge model, but the way you train the model is very sparse, very sparse. And that's also the ideas. So by sparsifying new networks, they're able to scale up the language models to be at very large scales. And I also highlight a couple of like popular language models people use each expert in industry at the moment. Let's say GPT-4, Gemini, and also Mach-1. It's also the ongoing work we have with Microsoft. We're trying to improve their language models and so on. And in this work, we actually propose a competition mechanism to improve further how to buy experts. Okay. And perhaps also very popular application nowadays, like how can we build like a large multimodal models? Let's say you have like different type data, right? You have time series, right, over there, and you have you have text, right, from doctor, right, and you have like medical images. So we have different type modalities, and it's very hard to build a unified model of the type data because we know right the way we actually handle each type data is very differently, right? That's why we think about a way to build like a pre-trained models, use one, able to learn everything from data. And the idea is that we think about using each expert. I mean, like each expert going to handle one type data. Okay, let's say one expert handle like time series, one expert handle like text image, and so on. So the idea is like we try to combine the strength of each expert. Right? In this, for example, this one, like we have like three type data, and we come into like models when we have a gating. Gating means like they go to assign a weight type data. So after we combine them, and we have each expert handle one type data, and we have the final data, this one, output over there. They try to basically learn everything about like time series, language, image, and give you like an output actually able to account for all the type data. And this is actually ongoing work between our group and Harvard. We try to basically use that kind of thing for like healthcare data. Okay. It's also like based on like one work that we already finished and on like one ongoing work. And the final one is also in collaboration with Toyota at the moment, and we try to use Visual Expert to enhance the safety of like vehicles. So the idea is that nowadays, when you try to use like autonomous vehicles, then we have 6 cameras, uh, 6 views of like car. Then the idea is like we want to have a very high quality image, right? Because like if you want to have a car, right, AI models in the car, and when you want to like detect some objects, right, then we want to make sure that objects appear on the front view going to be consistent among different views, right? This means like let's say you see like a people over there, some people here, right? Then it's make sure like you also see the same people in some other areas of the views. And the challenge here, like if you don't have enough data to train like the AI models, then perhaps the images that you generate from like are going to be problematic. So that's why at the moment, even Tesla and Toyota, they try to think about a way to generate more image. And also the multi-view, mean like we have 6 views of images and make sure that all the images going to be consistent. Mean like the object we see in different views going to be consistent. Let's say you have like some people here, yeah, it's yeah, over there too. Like because like it makes sure like the car can detect the same objects like in different views. And the idea that we actually develop is we use each expert, where each expert capture like one view, right? And we also use diffusion models to generate images. Similarly, we have a picture expert, where each expert handle one view of like a camera, and we have diffusion models to generate data each view, right? That means like we have like combinations of picture expert and diffusion models. For example, these are the results that we have from like our models. You see that we have views. And we can guarantee that we have consistent series of options. Let's say on that for the left, we see the unit, right? And this one also have the same unit. And same thing, even that one, we see the same tree. The reason is important because when you basically have a car, right? Then we want to see that even in the very challenging conditions of the weather, then we have the same system objects that the car can detect along the way, right? And this is very crucial to guarantee the safety of the car. So it is also like ongoing work that we have at the moment with Toyota. We try to improve further like the performance of like these models on generating like multi-view images.
So what is the expert?
Expert basically like expert like each view model, like each view, right? They have you have 6 views, right? So each one capture one view. Yeah. Like you have like basically you have 6 people on your networks, right? Usually we only have one single people on network, right? Now you have like each expert has a people on networks, right? They capture this different view. Usually when you have 6 different views, you have go along the same models, right? Now we partition the different views, and each expert capture one view. It's very different than traditional diffusion model when you only have one people on your network to capture everything, right? Now we actually hope that each expert can capture one view outside the car. Just like the data, like you have like data, right? Because you want to generate new data, right? For like the AI model, right? Inputs like the data, images, right? And basically you have combinations of images. It's like the previous one, right? The previous applications. Oh, sorry. We also have like data of like time series, language, and what we don't know about type data, right? We put that into like models, and hopefully each expert can specialize one. That's what we right. Same thing here. We also have data from different fields. We don't know exactly which field. We put that into the models, and then we have expert to capture each field, right? So hopefully that because like, we have like diffusion models, we want hopefully that each expert can generate their own like things in the models. It's very different from the traditional diffusion models when you all have one model generate everything, right? But that's not going to work because like you're not going to have the consistencies of objects. But it's also like where just want to mention that this idea is actually also were used in the recent years in machine learning. Just like last few months, people also like think about using visual experts to improve like performance and also scalabilities of visual models. And here we also use this one to like improve qualities of images. 16, yeah. You can even more, depends. Like if you want to be like, maybe you have 6, right? One view for 6, one view for 1, right? But then you can also use more because we can think like, okay, we can have 2 experts, 100% view as well. It depends, but I think that should be like more better. Yeah, not yet, yeah, because it's like a ongoing project, so we don't have. I mean, I can't tell you much because like this ongoing project, so we can. But it's high level idea. Like we use expert to handle different views. It's louder.
How should we expect that these experts interact with each other? So, I mean, like, how do they
It's a good question. Yeah, very good question. So there, I skipped some details here. So actually, we also have like an extra step, right? I mean, I can't tell you much, right? But it's like, but the idea is like we protect because basically like we should somehow have like 3D information, 2D information of the image. So the idea is like we map the 2D images to 3D space to learn some features of these guys, and we map back. So basically, mean like when you actually have the 3D information, then it's actually going to expert. They can capture like some kind of like features of these objects.
So you have some like actually have like they map each other.
They map each other. Case out. Sorry.
Like we will have some that's the like the simulating, so we like the answer maps.
No, we don't have any. We just basically have that's 3D steps. Because like I mentioned, like if you don't have that step, then perhaps buildings here are going to be something different from that. We tried before. Let's say we have this building here, right? But then right, this one we have something like tweet. Because they can detect. Even like you have like an SUV, right? But then let's say this one is like positive, right? Let's see that this one is SUV. But then by doing the 2D, 3D, we're able to capture the depth also of objects. And also like the
But what I mean, the depth side. Just like if there is some anchor point of that, this side, or this.
we just I mentioned we use a 2D to 3D step. I guess this is also what you mean. This also capture what you mean, yeah.
I understand like in this field of when you do generations,
Mm.
there's a lot of previous work. They put that the different model already have a good correspondence.
Mm.
Correspondence between multi-views, and they actually use a lot of intermediate representation in 3D, such as Gaussian splatting or the points, and they prove like really good accuracy.
Yeah, I see your point. Good, yeah.
Use the visual expert instead of using the intermediate
Yeah.
representation like that.
I think you only have I mentioned right. The thing is like you don't have consistency of like a depth. Let's say you have like different cars, right? The depth of the car, they don't see that. They can only guarantee you have the same car, but not the depth of the car. See your point? Yeah, this is what I mean. And also one thing like expert also can improve the scalabilities of models, right? Let's say you need to have a huge model, right? Whatever, right? And you can use the spark expert here to improve the scalabilities. Right? We can just apply it. Okay, so yeah.
Most problems in they actually use autonomous is because it's expensive into the high quality multi-view image, and so I wonder that if you use the visual expert, usually to use to train the one of the experts from scratch, or you just use the is pre-trained already.
Good point.
And what is the difference between the expenses of the using the virtual expert? Because I believe that virtual expert require a lot of computation resources.
So we use sparse ones, you know, like basically you think you only just like top one. Let's say you think you have this skill, right? But you basically you have only top one. You only activate one expert train. You don't activate all of them. So I mean like that one, let's say you have like the image from the left, right? And it's actually a specialized one only.
But I think that you need to have the influence without approve experts.
Yeah.
Which expert to evaluate?
Yeah.
Which expert is better?
Yeah.
And then also you said that you use the diffuse models, I think. Because models time computation.
Yeah, that's why. Yeah. But like but then, like I mentioned, right? Top, if you use like let's say if you have this one, right? If you only top one, then the cost of computation essentially lives similar to the diffusion model. Like so you only activate one expert to train, right? To the size of whole model, basically just like a single diffusion models. So the cost is similar. But then you allow more specialization of expert in different fields. Point.
So it's feature.
Just like from scratch. Even but I mentioned it's similar, cost similar to when you train a single diffusion models. Because like you only activate one expert. I mean, like let's say you have like different fields and they look at the pixels on that one, right? And see which one is going to actually train. So the same thing. So let's say the expert one handle like the first view, right? Expert two, second view. So when they look at the images, they have the weight for each image. So let's say if the weight for the image is like very good for like very high for the first one, they only activate the first expert to train. And they actually close like the freeze the remaining experts. Yeah. Because I mean the training cost is similar to when you have like a single diffusion models. But then the hub is like, oh yeah, great.
Well, since you're on general question, want to go back to that slide.
Oh yeah, correct.
So what's the output? I mean, this is an combining images or combining text is rubbish. You've got to combine like logic.
Yeah, we need to, I mean, map that into like some RD space, right? RD space, right? I mean, it would, right? But it would. We have something like
yeah, but I'm talking about the output.
I would like combination. Let's say expert one is RD, but two are ID, or one. So we actually have the same space for.
Oh, so the only one expert is
Activate.
Yeah. So it's not a traditional software.
Yeah. Not active top one. If you top one, like only best one, only even top two, something like that. Okay. Yeah.
One expert is activated. Not enough time because our data will go to the active work. So that would be like so if our batch is large enough. So if so for example it consists of 10 students.
Okay.
So because we only flow to one active first, so but if it's too large and it's just like 5 token is go to
That's one. Yeah, what I mentioned is like load balancing. Like some experts may handle so many tokens, so they actually have some extra loss to actually guarantee the balance of the tokens. And I skip the things. Like they have some extra loss function, right? Extra regularization. Make sure like the block can go to choose expert. Yeah, they still like let's say you have some extra loss function, right? That allow like expert to choose the proper one. Let's say you have 10 tokens, right? You have 5 experts, and you have some extra way to let the token to only choose like 2 experts. Each token, yeah. But you're going to have like 1, yeah, every. This is a trick, yeah, because loss balancing is very important on these things. And this also affects the performance of like this model, right? And that's actually a huge effort people use focus right now, loss balancing. Is this clear? So yeah, we basically do just application there. Now we actually mentioned like some topics that people consider at the moment. This is only a few topics I mentioned because this area is very popular at the moment. But in my opinion, there's 4 challenges. The first one, like I mentioned, how can we guarantee that each expert is specialized in their things? How can we basically guarantee that we have the expert and the actually specialization of expert are different, right? You don't want 2 experts to specialize something. It's it's basically a waste of memory, right? And the second thing is like, how can we understand which expert in these like massive networks? How can we publish their behaviors? And third one, it basically come from like the safety, right? I mentioned like if you get an expert in these like AI model for car, let's say, right? How can we guarantee that they have like a robust and safe? And finally, also scalability, which is for like massive AI models. How can we develop effective smart expert for these like large scale AI models? So these are basically like the four challenges in our opinion. And I also want to give a brief overview of our group contribution in the last few years on that topics. Basically, we have efforts on the 3 fronts: theory, method, applications. For theory side, I mentioned we focus on understanding the expert specialization. Like we have like this is all still like ongoing works that our groups focusing on. And then for the method, we focus on like building like effective Scrum to expert for AI models. And finally, for applications, we focus on like large multimodal model, right? And also recently also consumer. And only 3 topics we still we have a lot of like ongoing projects. Just want to mention that this mutual expert area on AI models is very active and hot topic at the moment. So for the talk today, I only focus on 2 expert topics that our group finish. The first one I mentioned, expert specialization. Especially we want to see like the effects of the old programmatization on the behaviors of experts. Right? And second things like there's one phenomenon that I just mentioned, like when you have a sparse one, then the expert going to learn the same thing because like they're not specialized enough, right? So this means that the expert not have good specialization. So we have collapsed experts. Like this means that like all the experts learn the same thing. Let's say you have like image text, when all the experts going to only learn the image, they skip the text. Right? So it's not good for the whole models. That's why we have 2 issues. The first one, like how can we understand expert specialization, especially in the context of transformers, which is the cornerstone in learning in the last few years. And the second thing is like how can we mitigate the collapse experts, right, in like large scale AI models. So for the first direction, we understand the expert specialization. It's actually consists of multiple actually, but we are only focused on 2 works that we finished this year. Actually, only a few months ago, right? And even ongoing, we try to understand like cell attention in transformers, right? Using mutual expert to understand like why cell attention is good and any way to improve cell attention by using mutual expert. So in case that you're not familiar with transformers, but this basically like the state of the art, right? And also cornerstone of deep learning in the last few years. So the idea of transformer is that we replace the standard bit over layers by the self-attention. This is the difference between like traditional LibNet and transformers. This is basically the extra attention layer that really make transformers stand out. Okay? And I mentioned, but then the challenge here is like, how can we understand self-attention? Because in high level, self-attention helps us to learn the interaction among like the words tokens, right? In like a sequence of words or like and so on. But then when you try to learn the scores, we try to see like which word I'm going to attend to other words because we want to predict the next word, right? We want to see what are the important words in before that actually going to determine like the next word. So we try to study about the score of like these like tokens. And tokens here mean like the words in a sequence. But then the self-attention gives us a way to compute the scores, right, of like the tokens. But the question is, how can we understand that self-attention going to give us like an effective way to assign a score, right, to like the token, and how can we guarantee that we get the best token to predict next word, right? So basically, these are like the key questions because people use self-attention all the time nowadays in applications. But the remaining things like how can we interpret self-attention, and well, it's actually the best thing we can have. So to actually give a better way to understand self-attention, I also give some math. But you need to worry about math. So basically, ideas like I mentioned, the main difference between like transformers to the traditional like LibNet is that we have that self-attention function here, right? And we also have a C connection plus Y here. And connection here is guaranteed that we don't have the vanishing gradient when we train, right? And for self-attention, then we have 3 components. QKV, right? Q stands for the carry matrix, and K stands for like key matrix, and V stands for the value matrix. Right? So basically, you have three linear mappings of data to like some manifold, right? And it helps that the Q here, basically QK here, basically trying to learn like the interaction among the tokens. Like let's say you have a sentence, right? You try to learn the connection between words in that sentence because you want to predict the next word of that sentence, for example. Then you want to see like what are the most important words that are going to help us to predict the next word, right? And basically that submax going to assign a weight for like the words in that sentence, just that we can know which word going to be important for the prediction, right? And the value basically give the same scale for that word. So for this, like basically we have that like ALY here is attention, and we're going to use the same notation for the whole talk, right? The ALY here is for cell attention. And I guess like you may have question is what is the core idea behind science? Right? How can this going to guarantee that we can learn the best attention of words, right, of tokens? How can we make sure like this going to give us like the best way to predict next word, right, based on the previous tokens? So this also basically still like very like challenging problems in the community. I mean, even we use that nowadays on most applications, but then we know exactly the meanings of cell attention. So in the talk here, we're going to give a way to understand cell attention by using image of expert and also show us some way to improve further. So you can ignore like the previous formulations. Now we only focus on the next. So basically you can show that because for the attention, right? The big N here stands for numbers of tokens, number of words, right? And the AL here is in a matrix, N by N, right? N by D, sorry. So we mean like we have like big N, which is stand for number of tokens of the sequence. And we show that each row of like cell attention is essentially a mixture of big N expert. I mean like we have, let's say you have 10 tokens, it's mixtures of 10 expert. And each expert is a linear function, right? It's a linear expert. Basically combine the expert, and this is like the way you combine expert submax. But the submax is applied to the second order one. Could be the quadratic function. I mean, like if you have the one dimension become y square, like time bij. So I mean, like we have gating function to combine the linear expert, and the expert here, linear expert here, mean like it captured from the three embedding matrices we have, right? WQ, KLB, right? So I mean that we can interpret the cell attention as combinations of expert, but then the combinations is basically based on using the quadratic gating. Okay. Any questions so far? That's a very important insight, right? It's been like if you want to guarantee that we have good understanding of the cell attention, that is also mean that we have good understanding of the meter expert when you have linear expert and quadratic gating. So in this model, what we care more about is like how to estimate the Rj and the matrix Bij. Because these parameters capture like the embedding matrices, the Q by KLB, which essentially means also cell attention matrix. And that's the way we actually try to see, because we saw that right for such kind of like models, right, then if you try to estimate right the Rj and the Bij here, because you want to study about the specialization of expert, right? It captures the attention of the words of tokens. Then we show that we need exponential number of data. We need to have many sequences, right? And we need to have like a huge number of data to guarantee like good estimation of the cell attention. It's been that even like you have like a sequence of tokens, you want to learn good cell attention. This huge number of data to do that, right? And it's especially impossible in practice. And that is used because you have the linear expert, right? The linear expert comes from the linear embeddings, remember, right? And that if you actually write it out this function, right, we have this like quadratic gatings, right? And also linear expert, very simple one, right? And we can easily verify that the first order derivative of that function u, right? And that function u just by itself are linear dependent. Mean like you actually able to find a way for the gradient when you train the models be vanished. Right? Mean like when you train the models, you learn about the R, right? Learn about the R, B, and there's situation when the gradients of the loss function vanish to 0. And it causes the singularities of the training. I mean, like the optimization, the training will be slowed down, and it affects the performance of the method. And I mentioned, it means like we have that, mean like you have and any optimization method, it really give you like good behavior for that. Like, let's say you have that have like Shorter convex, right? And you have super flat. Even you move the optimization method, it takes a long time to get there. So I mean, in most of the time when you stop the algorithm, like it's only give you some solution, but not very good, not very close to optimum. And that's because that means like optimization and learning become very difficult because you cannot get very accurate of the optimal solution. So in ongoing work with Microsoft, right? We still ongoing. We actually think about very smooth solution. So we think about using a non-linear expert. So I mentioned, right? The challenge actually come from a linear expert. We come from linear embeddings, right? So idea is like we can use like non-linear expert with the non-linear embedding. So we have like sigma here control that like the non-linearities of the expert. Like, and so I mean like if you look at the tension, right, then earlier we don't have sigma here. We only have B, UK, right? Linear embeddings. But now for our case, we consider non-linear embeddings. We have S of B. This one actually we have a non-linear expert. And its computation is similar, right? Only you have one edge of non-linearities for the V, right? So everything is similar, the training is similar. But we only add an extra non-linearities for the value. And we realize that by doing such, why it's important? Because when you look at that one, you can easily verify that the first order derivative of U bar here and itself are always linear independent. If you have like good sigma, like you choose like let's say activation in channel and so on, then you can guarantee that the training is going to be optimal. Like you recover like good landscape of the training loss and you have everything good. Generalization, performance, everything's good. By just adding a little bit of nonlinearities to the values of transformer. And I mentioned it leads to a shared landscape, right? And optimization and learning become much easier comparing to like original transformers. And we also test the result on some data. Let's say on out of 10, we see 5% improvements comparing to standard transformer, and by using like Trello, okay. And on ImageNet, like 2%. And we're still testing the result. That's why I haven't put everything here. And we try to test like the transformer very large scale, let's say a couple of billions scale transformers with that nonlinear expert. And the hope is that if it's actually work very well, then we can integrate that one into the current like language models that people use in industry. So it's basically like the first direction I want to highlight, like by just change linear expert to non-linear expert in like transformer self-tension, then we're able to improve a lot the generalization performance of models. And very simple trick, right? Nothing much, same cost, same training. Just like add a little bit of non-linearities to the embeddings. Yeah. Any questions so far about this direction?
But are we showing off anything of linear this non-linear approach?
Oh, I mean linear, yeah. I mean like when you actually linearize this one, right?
Yeah.
We haven't tried this one, but we think like it's also going to work as well. Like, oh, for that one, you have different gating, right? When you linearize, you actually have different type of gating function. I mean, it's pay, right? So I mean, like the gating is not going to be quadratic, right? You have only linearized. So that may need to have different conditions on the expert. So I mean, like even maybe for linear expert, the challenge in this case, right? The linear expert interact with the gating function. In your case, when you linearize expert, linearize the gating function, then it still have interaction. But at a point, like if you actually use like non-linear expert, then if you cancel that interaction, so in high level, it's going to improve also linear performance. But how much, I don't know, because it depends on how much it's going to interact with the like the linearize of that exponential function, right? It's clear. So thing is like when you use like non-linear experts, right? You're able to guarantee that even you go very further into the training loss, then it's still very good. And for your linearization of the gating function, you change the landscape of the problem, right? So we need to investigate the effects of that. Yeah, but then I think it's doable. It's like me to understand like how much the non-linear expert and the linearization of submax, right, going to be. If we understand one, then we're able to decide further how to actually choose the sigma. In our case, we're able to demonstrate that if sigma is sufficiently nonlinear, then we are good. But in your case, can we change the gaining function, which understand further theoretically how it's going to affect. Then we can decide an experiment test. Okay. Any other questions? Yeah. Yeah. Oh, good point. Because like what we have so far here, like we only focus on transformers self-tension. Basically we have like we can make a standard transformer, right? And to our transformer. Let's say we have like the one from let's see what we have, right? The new transformer. This is our new one. We have that submax and it's our new one. And we compare to the baseline when sigma is linear. Because we want to see how much improvement we have when you have like non-linear V to like the linear V. So we don't compare to CNN. We just want to see like how much is non-linearities of the values going to help us in improving transformer. Because eventually we want to put this result into like language models eventually. And these are just like some like simple experiment to see the effect of the sigma in the transformer. A very good point. We haven't get there yet. Yeah. So yeah, we're still testing. It's only the couple. I mean, these results are like a few weeks ago. So yeah, that's why we put like a very detailed experiment here, which to test the results. Yeah, I hope that we are able to have everything ready by next month. But let's see. Any other questions? Yeah, question. This guy. Very good point. You have very sharp question, yeah. Yes, because like here I skip that detail, right? But here we basically say that we have different roles, right? So they actually share the V among different. So I mean like we actually perform only tasks. We like different token, they share some tasks. Especially they learn how to attend to other token, right? And that's actually a bit different here, but I don't mention here. But basically like we actually perform only tasks, learning, right? Inside the self-action. Very good question. Oh yeah, good point. Yes. Expert still linear. So for the transformer, right, it's linear, standard one. And for our case, we use Chalu. Yeah, we use Chalu. Right? Chalu. I mean, like you have like Chalu for this. I mean, like for our transformer, right? This mean like the Chalu here. For the original one, it's V, right? For the original one, V. And for our case, it's mean like Chalu V. Compare Chalu V to like additional. No, we use the same expert. It's like we just add like non-linearity to the V. So remember earlier we have V linear, right? Now we add like something. That's all.
So it is not in package. So it's not just talking about this one.
Yeah. Oh no. You can actually write out this guy's which expert. Right. Basically, you can write out this one over there, right? Submax over there, but in terms of like this one. But the linear here become sigma squared. You have like the non-linear V, it becomes a sigma. So it's still need to expert number of problems. Like you have big bang, right? Number of problems basically mean like we say a standard expert. But the only thing we change here is like expert here become non-linear. Everything's still just generalized linear to non-linear. So I mean like, okay, if you have sigma here, right? I mean the linear function, you can write out this whole thing into that one. That one. They are similar. Like the okay, great.
I don't know how much more you've got. I don't know. So this is very different to what you did previously. Multimodal, different modes.
Yeah.
This is internal. This is very inside a 50 layer transformer model.
Yeah.
So it's entirely.
Oh, I mean like for different application I mentioned earlier, right?
Yeah.
I mean I do have one at the end. So this is just like correlation. You see like how can we improve even like this multimodal is a scalability, right? By just looking at only transformer.
So this scale, all right.
Yeah, it's like we just look at like only like transformer layer only, and we're not yet about other things. It's like how can we improve the application? Just look at transformer only. Yeah, like we can actually improve the method, like training marks only by from like V to like V the values. This is a self-action. Right? We have like a transformer right inside the applications, and we basically can modify a little bit and can still guarantee some and like improvements. Any other questions? Oh, okay, yeah.
Like, is there any qualitative result or talking to visualization?
Very good point. Yeah, we haven't had that. Yeah, I mean, we have that for sure, but like not at the moment. I mentioned this only a few weeks ago. So yeah. Okay, so for second one, we've also showed up by using the ideas that we have just have, right? We can also improve like the very important topic, right? Continual learning. I'm not sure anyone here familiar with that topics, but the idea is like you have a sequence of tasks, right? Like you train Sabaten, MNIST, image snatch, even language, and so on, right? But you want to make sure like when you train the next task, that it can still remember what you have in the previous task, right? Otherwise, basically you forget about what you learned. It's like our baby, right? We learn things and we also somehow remember what we learned, right? And the same thing here, we hope that AI models can still remember some features they learned from previous tasks, so that can improve the performance. So this is the ideas. But then how can you guarantee that when you learn new tasks, AI model can still remember something important things? And this issue actually was named a catastrophic forgettings, right? So one way to improve like the how to mitigate the forgettings right, of the AI models is by using the prompts, right? Basically, also somehow like we use a retrain models, let's say transformer models, to generate a set of prompts. And helps that by input the prompt right to the keys and values of transformer, then we can improve the performance of the AI models. I mean, and hope that we're not going to forget about different features that we learned from previous tasks. Because the prompt here are going to give us the abilities for AI models to remember some features of previous tasks. Right? So in high levels, this means that you have like a pre-trained expert, right? Let's say a transformer, right? And this is because we know right, from earlier, a self-attention can be understood as a feature expert, right? So basically, we can write down self-attention and feature expert, right? What we studied so far. But then we have this extra expert come from the prompt. The prompt we generate from the retrained models, like let's say, yeah. And the prompts help the task, right, to learn, to remember about the previous features of other tasks. So the help that by remembering the important features, then it's going to improve the performance of new tasks, right? Because we're able to learn, let's say we have like a task of learning the images in Cyber 10, and we learn from MNIST, right? Then we hope that some features that also can carry to like Cyber 10, because they have some similar kind of like representation, right? So that's why this idea. And one way we use like hope that it prompts, I mean the expert, actually each expert is a prompt to actually able to learn some important features of our task. And it's also very not and this problem also not so heavy to train, right? Usually only linear. That's why even you have like bigger models, but it's still similar to like previous model because you only have some extra prompt, very like only factor in ID, very similar to train. To mean that you have like a pre-trained models, let's say feature transformer, right? And you have an extra expert component prompt. So that ideas were used by the work of one right, in the city only last year. And they basically get this solve that result for these problems in multiple data. Right? Basically, like on the baseline we have so far, this work get on the solve that results. And the idea is that they use only linear gating. We like for the gating function here, they use linear. I mentioned right, linear time expert, right? You have submax linear time expert. That's what we have earlier. And it's actually problematic because I mentioned if we use like linear gatings, then we have optimalities of expert estimation. Because expert here capture the specialization, right? And because you linear function, I mentioned linear can be issues. And when you use linear gating function, then it's going to be suboptimal. I mean, like we need to have huge number of data to be able to get good estimation of expert, right? I mean, like it decline performance of prompt-based continual learning. So in this work that we just finished 2 months ago, we basically proposed idea. I mentioned, right? We think about non-linear. Again, similar to transformer, right? Linear doesn't work, so we think about non-linear. That's why we design that non-linear gating function. This one. This is connection. Thus, on alpha scale function and non-linear. So you like we add some a bit of non-linearities to like the gating function to guide like the training to good area for loss function. So it means that we can somehow avoid the vanishing gradients when training models, and also that non-linear function to the gating. You see, this is the previous work down in this one. Now we add a bit like non-linear to that one to have basically landscape of the whole thing smooth, sharp. So we know generalization better, and also performance get better. So I mean, like for basically for this kind of idea, then we can improve the performance of this problem, right? By very symmetric. Okay. And basically, we can demonstrate that for the previous work, right? Then if you're going to get like good expert visualization, you should have exponential data. And for our proposal here, non-linear things, it's actually optimal. We like use much less data to get like good estimation of the prompt and expert in retrained models. And that give a huge improvement in terms of the results. Like we test on our result for like to work with a baseline on continual learning, and we have like 6 different like pre-trained models, right? And you see that sorry, these are the 3 pre-trained models, and our methods here. You see that on the baseline for all of the criteria, we all have like good improvements over the baseline. And this one is the SOTA results, right? And you see that we have over 2% improvement over SOTA, but just get from linear to non-linear, because we improve the landscape of training, and it's also help the method to generalize better and get good performance. Right. So the story here, like by looking at multiple problems by mutual expert, we can easily improve them. Just slightly change right problem. Here to linear to non-linear. Very simple. No more accommodation. It's like more more non-linearities to the data. Any questions so far for this one? This especially focus on expert specialization.
So what's your limit? Want to maintain the stability and plasticity of your limit. So we want to add a prefix to name it. Okay, so why don't we just add a have classification to name LoRa to this?
Oh, yes.
For each type rather than doing the prefix to.
They actually have LoRa direction too, yeah. But then LoRa's the performance is not as good. Yeah. For this one, we have each prompt can specialize better. But then the thing is like at the moment I haven't mentioned right. If experts here is just a linear, like just like a vector, right? Not even like function of x input, right? What they use like each expert here for the prompt, they only use like maybe prefix tuning, they only have a linear function, independent of x. So because they want more models, lines model, right? With that much. But then question now is if you change expert to something more complex, let's say a linear, but you have a low rank, let's say you have this guy, but he beta is low rank for the expert. Can you improve further? Because like at the moment they have very simple expert for the prompts. Like, question is if you ask this slide better, more complex expert for the prompt, can you get better performance without increasing the cost innovation? Let's go back to the question low round also the same purpose, but this performance is not as good. Yeah, we want to get a return model right by tuning here, right?
So second question is that normally for digital learning experiment, they will try to split the real the same data set into many tests. So
okay.
if we not use something the distribution sheet or any changing between the tests.
We do have the design, but we have recipe details here. There's some trick out there, recipe details here. There's some trick here. But I mentioned the core elements. We also have some trick here that I mentioned there. Thank you for the question. Thank you.
Model like this, the most important is the green gallery. Because we have to print on something. And test for some other later.
Yeah.
Please consider.
Good question. Yeah, very good question.
When I see in your experiments, because we use all the cipher and the Irish net and split later to train. And if you use a random something, it will be some high correlation. I have
High correlation,
the
high
data,
correlation, yeah.
the split is IIE.
Yeah.
And thus, I think that the comparison is not fair. I think it is better if you use some dominant concept like dominant or something like Inacta or PLCS. I think it is better. For my opinion.
Okay. Yeah. We can apply. I think to understand better. Apply. But there's also.
So between diverse more.
Yeah.
So your robustness of your algorithm more. Because if you use just split data set, all of the data they just train from my opinion, they just train from the small set of data and not show the diversity of the experts.
Yeah, it's a very good question. Yeah. You can try apply later. I think we don't have much time, so I need to move on. Okay. So the second thing is actually for the scalabilities of massive AI models. So it's also ongoing work with like Microsoft Research, AI. So and we also have like one finished work earlier, and here we try to use this idea for like the ongoing like language model we use now. We try to integrate one to like the models that are used at the moment. So right now, so far, right, we talk about like mixture expert without any sparsity, right? I mean, you on the experts. But I mentioned the core ideas behind the massive AI models, like we use only top expert to train, right? And that's also the core idea. I mean, like you have a bunch of like expert debating function. So let's say you have like one house expert. But then you only want to train 10 experts. So the idea is like you just to like top 10 values of the weight and then truncate the rest, right? And you normalize this way and truncate the rest. This is the idea. So that's why I really have the truncate. We like see the top K values of the submax values and truncate the rest. So basically this is the proper definitions. You to like the top values of that submax and you truncate the rest to be 0. That's the high level idea. So I mean, like if you have like 10 experts, right, in like the massive AI models, and you have top one, I mean, like only train one expert at a time. And it's also core ideas that people use in like let's say the language models nowadays, right? They only use top one. I mean, like this case, I mean, like it choose like the top one of the weight, right? The router, you mean like choose top one of the weight, and then it just train these guys. Let's say this is a token, right? The more token go inside and see that the second expert has the highest weight, they only use the second expert to train. And then when you have the token parameters to go inside the models, then the first expert have the highest weight. That's why you just turn up all the expert and you're the first one to train, right? This is another idea. So I mean, you only use one expert to train at a time. I mean, the cost computation is similar when you have a single feature neural network, right? Because you only train one expert, even you have a bunch of experts, the same size, right? And at the moment, what they will use in industry now is either like top 1, top 2, and nowadays top 4. Because they show that these top 1, 2, and 4 are optimal for the resources and computation. But then if we ignore about these engineering things, then one thing that really, two things really stand out in the Spark expert life. First thing is like I mentioned, right, the collapse of expert. Because when you like top 1 or 2 values, then it may happen that on the expert going to learn the same thing. Because some experts learn everything and the rest basically nothing. Or like all the experts share some similar things because they don't have enough training, right? Eventually they learn similar things. And it's mean that you don't have enough specialization of experts and the performance is not good. And the second thing is like more, I mean, the second thing is deeper. like if we want to actually understand about how experts specialize things, then it requires like a huge amount of data. Because usually we over-parameterize the models. Let's say you have a set of billions parameters, right? And it's very sparse. So we usually over-parameterize the models. And it's also affect the way we actually train these models because it's so over-parameterization, right? And then we require a huge amount of data to learn about these parameters. So basically, you have two issues. The first one, like collapse of expert. Second one, two things like expert specialization become challenging to study. And it's also based on like some ongoing work that we have with like my group and also like Microsoft AI. We try to think how can we improve the spark expert in like massive AI models. And high level ideas about issues like, let's say for the collapse of expert because of K values of submax don't really mean about the important expert. Let's say if you go back to the definitions, you see that the parameters that you have for the submax and the parameters you have for expert, they don't share, right? For expert, you have EI, and for the submax, you have a data, right? And they don't really share, right? So I mean, like even you have top K values of a submax, don't really mean about the important expert, right? We only see the we only train like say submax, and you don't really see about why is the expert important. So we need to find some way to really put the information of expert into the submax. Because right now, the parameters from the submax and the parameters from expert, they don't share. No way you really think about is important or not, right? So that's mean like we need to find a way to develop new way, right, for the submax that can indicate the important expert. And second thing is like for the optimalities of expert specialization, then we have interaction between gatings and expert. I mean like for the scaling and for the expert, when they train the parameters, they interact. So I mean, it slow down the training and get to some bad areas of the training loss. So the idea is that we actually developed last few months based on using competitions among experts, which is especially very popular. So idea is like you put information of the expert inside the submax, right? So we use like num, just any num of expert into the submax. I mean, like you rank the values of the expert inside the submax. Earlier, right? Earlier, we only rank like the values of data, right? And data and the parameters of expert, they have no interaction. But now we directly push like information of expert into the submax. So I mean that top K values of submax going indicates the top K of the expert, right? Because now like expert truly important, right? So very simple. And that in the name one million you top K neural responses. And we actually term our method to be like competition among the experts. And it's an ongoing work with like Microsoft AI. So a high level idea is like if we have such like top K values of experts, it can eliminate all the issues. The first thing like for the collapse expert, because you choose the top one, you truly choose the top one, right? That's why you able to guarantee the experts to truly specialize things, right? And second things like for estimation of expert, and we only requires like optimal number of data. I mean like you have most data to train expert comparing to the original one. And in high level, because I mentioned, we don't have any linear independence among the expert and the gaining function, right? And second things like the top K values of submax based on the values of expert truly indicates the important expert. And we also test the results on like language test, sorry. And at the moment, we only have like small and medium scale, and we still working on like huge scale in the several billions parameters. But we see that by using our method with different architecture, right? We see that our method, let's say the complete SMOE, have like better performance than on the previous method on this data. And again, I mentioned the improvements basically come from the fact that the competition, right? The top K competition, top K values of these expert able to choose like the good one. So it mitigate the collapse expert in the training and also improve the performance of like the results. So there are actually some future directions that I mentioned, like we try to improve further this model to somehow put that in like the real AI models. So basically, the first one, like we try to develop complete SMOEs in truly large scale AI models, I mean like several billions parameters. And from what we just got a few weeks ago, like we truly have a very promising result comparing to, let's say, the standard spy movies in language models. And second thing is like we can also put a nonlinear function of the expert into the submax. I mean, earlier we only have like f to be linear, right? And now we also want to put like nonlinear function of the expert. To help with that nonlinear function also can smooth the landscape of the training and can also lead to a better performance, better generalization of the results I mentioned. And this is basically two directions that we have at the moment with Microsoft AI. And that's all for my talk today. Thanks, everyone.
I guess we a bit over time, but
Oh,
is
yeah.
it okay if we can take
Yeah,
some
good.
questions?
Yeah.
So I think we open the floor for questions from offline, and maybe online
Okay.
audience. If you have any questions, you can also.
Question? I'm not sure.
Okay, there's one question from online.
Large experts result in sparse models. So there's a question by Tung, right? Large expert result in sparse model. What do you mean by large expert, Tung? Can you hear me?
I mean, like the expert with a
You
larger number of
volume
parameters. That's what I mean.
out of yeah, battery or something. Sorry. I can't hear you. Can you type?
Yep. See. How you turn on your volume?
It doesn't work because you have this kind of yeah.
Okay.
So it doesn't work.
Tom, can you try to speak up? Oh, yeah.
Yes. Yeah. Can you
Okay.
hear?
Oh, I mean like expert with large number of parameters. I think like the sparsity I mean here is like I mean when you have multiple experts, you only consider like the top ones, not the sparsity that you mean when you specify the expert. It's the different things. I mean like even you let's say you have like 10 million parameters and you have one expert, right? Very sparse one. Then the behavior of a 10 million size expert comparing to like 1 million expert, but sorry, comparing to like 10 dense expert, right? Each have like 10 million. Then I think thus when you consider the top one of the 10 million expert, it's better than the one with the sparse number of parameters when you have 10 billion. This is the, I mean the sparsity here not from like the neural networks, but from the combinations of neural networks. Is this clear?
Yes.
Yeah, okay, that's okay. Can see. Yeah. Hit type is okay then. Any question from the audiences?
Questions. Yeah. So first, come back to the part of continual learning. So I want to ask why you keep the linear term when we just.
Wait. Sorry, yeah, this one. Oh, it's a good point. Because the vanishing gradient.
Yes. So I want to ask why you keep the linear term in the visual getting function. Not like the one in when you talk about the. Yeah, linear getting on just now.
Very good point. Because when we train this one, we see that the gradient this one vanishing, and we actually get a trick from like because the gradients become close zero, and you can beta with that one. So we have exponential term, remember? And we realize that when we actually add a bit of like linear term, it's still the same scale of data. So that one can have because when the gradient beta, it's always x sigma. X actually sign all we control with exponential of law. So the gradient is still in control. If you don't have this one, it can go up.
So it can help in the case that the second term is vanishing.
Yeah.
And I want to ask a second question. So I think that the visual expert can we think about it like the dropout in neural networks, but in a larger scale?
Yeah, actually there was actually connect which expert to like dropout there. Some type dropout there. I don't remember exactly the combination, but they actually works actual connection between the two. Yeah, I also can just apply the same. Sorry? SMA, okay, sure. That's fine. Yeah. The values of expert inside of that.
Yeah, but in the seniors, and that's we don't rest.
Yeah, that's why when you rank an expert, right? And you truly choose an expert, right? Let's say you compare the expert, the norm expert, right? Norm expert, the side expert, right? Which one actually have attribute values mean more important, right? I mean, you truly indicate the important expert into the submax.
That is what we do too.
We also have like some type of balancing thing again. Okay. There's something that's somehow balance that one too. Yeah, I see your point, yeah. But I mean, I skip the details. Okay. We must make sure like we don't choose expert multiple times. I mean, everything in talks so far, I skip some detail about how we balance the expert. It's not only thing that we train. We also have something.
We have to negating well, just response of all.
Good question, yeah. And so it's mean like we actually lose that top one here. So the idea that we actually only turn on this. Let's say you have 10 layer, right? We only use this one for one layer. The rest are still like traditional step one because this only add a little bit more, right? And it is also one bottleneck we try to improve at the moment. How can we somehow like because now we actually when you use like for very large models, that's a 64 expert, like 128 expert, then we see that it's actually a bit more expensive. So we try to see like decide that one better. But a good point there because good points like when you can use this kind of everything. So you use like that one. You only train one. But now we only use this one for one layer. Okay. The rest are still like traditional spline. And we also have a method like we only we have like some kind of like costing coin, right? 100% we actually train this one and the rest we train the traditional one. So we have different strategies to actually improve computation and improve the behavior at this point. Yeah, but thanks for the question. Oh, so I mean, especially given the norms, the values. I mean, you have the norms. Depends. Okay, question, Fred.
Then look forward, right? And there's also the explanation.
Exponential. This exponential. Submax.
Yeah.
So, submax of the values of expert and expert. Submax of non-expert. Yeah, you just basically put that one inside there. Yeah. Yeah. Because like we argue that if you only value gatings, then it's not really indicate the important expert. It doesn't really indicate that. Yeah. So we try to use like the expert directly to the gatings. And people mentioned like theoretically it's also landscape also smoother and sharper, right? So optimization even easier because like when you put this one here, when it takes my derivative theta, right, then the gradient of this is often much better than traditional training. The other thing that is like a mentioned, then we need to be on expert, right? When you okay with the message of use that one. But this is ongoing work to try and improve computation. Okay. Okay.
We talk about like the representation collapse because when all the experts trying to represent the same thing, but as far as I understand in the machine learning, there's a lot more trying to improve the trade-off between memorization and generalization. Basically, it's like when the model will have enough parameters to memorize the Fourier type, they will learn some kind of abstract representation in each neuron in the way that it can be generalized. So do you think that this kind of representation collapse actually like a hint for generalization because it cannot memorize the Fourier type?
Yeah.
So we cannot like interpret the representation in each level.
Yeah. Good point. Yeah, exactly. Because they cannot actually memorize everything, right? But you don't have theory for that. It's very difficult. Very difficult. But I think that is indicate that for sure because performance vary a lot when you have collapses like expert. Yeah. But when you actually able to make sure expert actually more diverse, then I mean there's actually a lot of work on it recently, right? They try to diversify the expert, and they see that even like in large scale models, performance better, even in on test sets. Right? So it truly means that generalization better. But theoretically, we don't have any. But I'm sure that is what you just mentioned, right? Correct. But we have proof for that. Because we have mixtures of new network, but not a single one anymore. The theory for that is still very challenging. Oh.
Sorry.
Yeah.
Yeah. Question.
Yeah.
I still wonder about the rationale behind the real response is because just make an example where you have a classification model and have 10 class, and so the expert, it means that the best expert, in my opinion, it means that the expert that have some time reliability on some class. For example, like you classify one class with more than 90% and other classes really low.
Okay.
So if I take notice of this one, I think it will be a little bit lower compared to that with the norm of those with all of the 0.1, 0.1, 0.1. If they have report into the
Yeah, I see your point. So I think the meaning is a bit different here. So let's say you have X input, right? Let's say you have image. Let's say that. Yeah, pixel. Let's say your pixel here, right? Face. So this one I'm going to indicate where it's from here, nose. And let's say this X pixel from here. So that one basically try to rank expert. Which one? That's like what it means. So it's not like one.
yes, so it's not a misunderstanding because it is inside of one model.
Yeah. Okay.
And it if I reflect the pictures
Yeah.
applied to the project itself,
Mm.
or that what do you think is the expert?
Yeah. Yeah. Yeah, I think it's good. Yeah.
Right, thanks for all the questions and thank you again,
Yeah.
Professor, for giving a very comprehensive and interesting talk.
Yeah.
So if you would like to ask more questions, feel free to approach him after the talk.
Mhm.
And thank you again for coming and
Yeah.
hope to see you again.
Thank you. Yeah. Thanks everyone. Tắt nhé, tắt được không?
Yeah, I stopped recording already.